In this section, we're going to take a look at some more story problems that involve the law of sines and the law of cosines. And the ones on in these class notes are a little more complicated maybe than the ones that you saw in the video notes. So I think it'd be really good for you to try to make sure that as we go through these, you again pause the video, try it yourself, try to figure this out on your own before taking a look at my solution. So I encourage you to do that with each one of these examples. All right, so in example one, it says that a pilot sets out from an airport and heads in the direction 20 degrees east of north, flying at 200 miles per hour. After 1 hour, he makes a course correction and heads in the direction 40 degrees east of north. Half an hour after that, engine troubles force him to make an emergency landing. So we're going to find the distance between the airport and the final landing spot, right? So obviously if a plane is having trouble, it would be really good to know where exactly that plane landed relative to the airport. So again, as we do often, let's sketch a picture. Let's do what they started off with, right? We head off in a direction 20 degrees east of north. So remember, what we want to do is kind of make a due north line and then say, okay, let's go 20 degrees east of there. And we're going to fly for a while, for an hour, right? At 200 miles per hour. And then from there, we make a course correction. And from there, we go 40 degrees east of north. So, that's got to be a little more of an angle there, 40 degrees. And so do something like this. And I'm going to make this side shorter because we only go for a half hour here. So here, this distance is 200 miles, right? Because I'm taking 200 miles per hour times 1 hour. And then this one, of course, would just be 100 miles, right? Since we're taking 200 miles an hour times a half hour. All right, so we have those two distances, so that's good. But what we're really interested in is we want to find the distance between the airport and the final landing spot. So we want to calculate this distance right here. So we want to know D. All right, so we know these two sides. And we also know that we can use the law of cosines if we know two sides and the angle between them. Then we can easily find the opposite side. Okay, so then the question is, they don't give us information about any of the angles inside this triangle. So I think the question would be, can I figure out, using a different color here, can I figure out what this angle is here? If I can, then the law of cosines will make this work really nicely. All right, so let's see what we can do with this. One thing that is often a nice thing to do is when you don't have direct information about some of your angles is try to make some 90-degree angles. So I'm going to draw a line from here to here to make a 90-degree angle there. And the reason that that's helpful to me is because I know that this here is 90 degrees. So I got 90 degrees here, 40 degrees here. So if I can just figure out this part here, then I'll be able to figure out my red angle. Okay, so let's see, do I know it? Well, yes, I do, because this is 90 here, this is 20, and so they all have to add up to 180. So I actually know that this is 70 degrees. And I know that because it's got to be 180 degrees minus 90 degrees minus 20 degrees. Okay, but then if that's 70, we know that all the way around here is 360 degrees. So I actually know that this is 160 degrees. How do I know that? because it's got to be the total 360 minus all those other angles that you see, which gives me 160 degrees. So that's great. We know this angle. We know these two sides. And I kind of covered that my 200. So let me rewrite it here. So 200 miles. So I know that D is going to be equal to the square root of, so the two sides squared, so 100 squared plus 200 squared. Then we're going to minus 2 times those sides multiplied together times the cosine of the angle that's between them, 160 degrees. And so that, I could simplify that a little bit. This is going to be 50,000 minus 40,000 cosine of 160 degrees. And that gives me that the distance is approximately 296 miles. And it's important in all these problems to make sure that this does make sense, right? If this is 200 and this is 100, you know, this distance should be greater than 200. So 296 seems like a reasonable answer to me. All right, it asks us the second part of this, though. It says, find the bearing from the airport to his final landing spot. Okay, so bearing means, right, we want to say like, okay, from due north or from due south or from due east, how far do I go, either west, east, whatever direction we want. So it seems pretty natural to me if I can just figure out this angle right here, that will tell me my bearing. Okay, well that's great, but if I can just find this smaller angle in here, okay, this red one, then I'll also know that bearing because I can just add 20 to it. So let's work on finding that red angle. Well, at this point, I know all the sides, right? So I know 296 is my distance. So I can use that. When I know all the sides and I know one angle, then I can always find other angles by using the law of sines. So what I'll say here is this will be the sine of my angle divided by the opposite side from it is equal to the sine of 160 divided by the opposite side to it, which is 296. And then, of course, I can work on getting the sine of theta all by itself. So that's 100 times the sine of 160. You know, and since we're not dealing with special values anyway, I would suggest don't even worry about simplifying. We're going to just crank this out in our calculator anyway. So theta is going to be the sine inverse of 100 sine of 160. And of course, make sure you're in degree mode as you're doing this, right? Which gets me 6.6 degrees. Okay, and that seems reasonable. So at this point, though, we got to remember I wanted that bearing, right? So I wanted that green angle that we're talking about. So of course, that's 20 degrees plus my 6.6 degrees. So I would say 26.6 degrees east of due north. And of course, where's that coming from? Just 20 degrees plus 6.6 degrees. All right, so let's take a look at a couple of other problems here. It says, from 2 points 400 meters apart on the bank of a river flowing due south, the bearings of a point on the opposite shore are 28 degrees east of north and 32 degrees east of south, respectively. How wide is the river? Okay, so it's from a point, so we're talking about a particular point on one side of the river. Okay, sorry, 2 points on one side of the river, and then we're talking about the bearings of a point on the opposite shore. So what we really want to have here is, first let's go ahead and sketch our picture here. Maybe we'll use blue since we're talking about a river. So we've got this river. We know it's flowing south, right? That's what they tell us. And so this idea is we've got these 2 points 400 meters apart. So let's label them accordingly. So these ones here. And then we're saying that to a particular point, on the other shore, we have these bearings of 32 degrees and 28 degrees. Now I'm already looking here. If I draw this angle, that to me looks bigger than either 32 or 28. So I'm going to just, for the sake of being a little bit more accurate here, I'm going to correct my picture and make this river go down further, and then make these points further apart. That'll make my angles smaller. All right, so we're going to some point right up here on the other side.
So if I draw this line from here to here, that is our 28 degrees east of due north. And then this other angle here would be our 32 degrees east of south.
And we know that these 2 points here are 400 meters apart. And then finally, what are they asking us for? They're asking us how wide the river is. Okay, so we're assuming that it's pretty uniform width, at least through the area we're talking about. So what we're just going to do here is say just straight from here to here, that's the height that we're talking about. All right, and so as I look at this, the height is definitely a side, but it's a side of a right triangle. So, I might be thinking things like, can I do right triangle trigonometry in order to figure out this height? The problem is I don't know anything except this 32-degree angle or except this 28-degree angle, right? In order to use right triangle trigonometry, I would need to know either this hypotenuse, or I would need to know this side right here, this adjacent side. And I don't know either of those. I know it's 400 total from here to here, but I don't know this length. So what I do know, however, is if this is 28 and this is 32, then I can figure out this angle right here. So I know that that angle has to be 120 degrees. And the reason, of course, I know that is because total, it's got to be 180. So if I take that minus 32 degrees minus 28 degrees, I'm going to get 120 degrees. All right, and I know the side opposite that 120 degrees. So the answer to our problem there is that, we wanted to know sides of the right triangle. Well, I can figure out one of the hypotenuse sides by using the law of sines. So I can say something to this effect. The sine of 120 degrees divided by 400 is going to be equal to, and doesn't really matter which of these we choose. I'm going to choose 32 degrees. So is equal to the sine of 32 degrees divided by, and I better give it a name, let's call this one x. All right, so I go ahead and do a little cross multiplication thing. So it's x times the sine of 120 is equal to 400 times the sine of 32 degrees. And then I can divide and get x all by itself. And when I do that, I get about 244.8. Now that's not my answer, right? That's just this hypotenuse. But now by knowing that that's 244.8, now I'm allowed to use right triangle trigonometry in order to actually answer the question. So I can say, for example, what do I know now? I know that I want to know the opposite and I know the hypotenuse. So opposite and hypotenuse should make me think sine. So I'll say the sine of 28 degrees is going to be equal to h over 244.8. So that means 244.8 times the sine of 28 degrees. That's my h, which is approximately 114.9 meters. So I kind of have to take this in two steps. We use the law of sines in order to put the problem in a position where we can easily then just do right triangle trigonometry. All right, one last example here. We have a pilot flying from Portland to Seattle, a distance of about 200 miles. She flies 20 degrees off course for 50 miles. How much must she correct her course by to get to Seattle as quickly as possible? Assume that Seattle is directly due north of Portland, just to make things simple. All right, so we've got our picture here. We've got Portland, and then up here we have Seattle. And we're saying that, just to simplify things, it's directly north to south, and then this is 200 miles. So we make, so she goes 20 degrees off course. Now, you can draw this however you want. If you want, you could, because it didn't specify, it didn't say whether she went 20 degrees off course this way or this way. I'm going to draw mine going to the west. Doesn't matter though. If you drew it differently, that would be just fine. And she does that for about 50 miles. So let's just try to kind of make that sort of, you know, correct relative to this 200 miles. So there's my 20 degrees. And so, of course, she's going to need to correct the course in order to make sure she gets to Seattle. So we're going to have to do something like this. Okay. So the question is, how much should she correct the course by? Or in other words, what's her new bearing, right, after she corrects? So what I would say is what we really want to do is be able to report this angle right here. All right. So in order to be able to do that, we know this side, we know this side, and we know this angle that's between them. Anytime we have that, we know that we can find the side that is opposite of that. And I think that that would be pretty helpful here. And the reason I think that would be helpful is because if I can just figure out what this angle is here, then I should be able to figure out the red angle. Okay? And the reason that I should be able to figure out the red angle is because I know that if it's 20 degrees here, because these north-south lines are parallel, this one also has to be 20 degrees. So then what I would have is that we'd have this angle plus the red angle would have to give me 180 degrees. So I'm going to get to work right away on figuring out what this side here is. Okay, we'll call it D. All right, but that's easy to do when we have the law of cosines. So 50 squared plus 200 squared minus 2 times 50 times 200 times the cosine of the angle between them, 20 degrees. And when I do that, I get about 153.97. Okay, so now I know that that's this side here. But then I can use the law of sines, right, in order to figure out this, right, this angle here, theta. So I can say that the sine of theta divided by the side opposite of it, 200 miles, would then have to be equal to the sine of 20 degrees over the side opposite of it, 153.97 miles. the sine of theta by itself. So the sine of theta is equal to 200 sine 20 divided by 153.97. All right. And then theta would be the sine inverse of all that. Now here's where we've got to be really careful with what our calculator spits out at us. Okay, so when the calculator spits this out, we get 26.4 degrees. Now that doesn't look right. We know that this angle here should definitely be bigger than 90. Okay, so when it spits out 26.4 degrees, what I can see here is that really I kind of made a mistake. I should not have said theta equals that, right? But this sine inverse calculation is important. So remember, what this goes back to is just like when we were solving triangles with law of sines where we had angle side side, we had to understand that there are two places on the unit circle that give you a particular sine value, right? So if I think about the unit circle for a moment here, what I know is that 26.4 degrees is right about here. But you get the exact same sine value over here, and what is this? This would be 180 degrees minus 26.4 degrees. So that is going to be my angle. So we can say theta is equal to 180 minus 26.4, which is 153.6 degrees. And that looks better, right? So this is a tough problem because we're kind of having to put together all these different things we've learned about. All right, so then what's this red angle here? So this red angle here would then be 180 degrees minus 153.6 degrees minus 20 degrees, which gives me 6.4 degrees. So what I can say is that she should go, so she should head 6.4 degrees east of due north. Now, if you had chosen to set up your picture in the opposite fashion that I did, so in other words, if your picture looked something more like this, where her initial going off course was to the east, then of course you would just say, you would still get 6.4 degrees, right? You would say she should head 6.4 degrees, but her correction would be to the west, right? Right, she would correct to the west. So you would say west of due north, right? And so obviously if there was a situation that you're answering a question that was kind of ambiguous, I would accept either one of those as good answers.